Hello, this is the 6th video of the 4th Graphs and Networks series on route inspection and the travelling salesperson problem for OCR Discrete Further Mathematics. And we consider further use of techniques to improve on a solution for the travelling salesperson problem. So, for the travelling salesperson problem, the term practical problem refers to problems that are not based on a complete network, where the weight on every arc represents the short distance vertices. If we apply the nearest neighbour to a practical problem involving a network that is not complete, it may fail, in terms of it may stall before reaching every vertex, or it may reach every vertex but then fail because there is no direct arc back to the start. So in this case, we'd have to go via another vertex to form the cycle. So, where we don't have a complete network, the nearest neighbour algorithm may still find an upper bound, but not always, depending on which vertex you start from. Let's look at this example and use the nearest neighbour algorithm on the network starting at B. So, B's nearest neighbour is A. Which is nearest neighbour to F, which is close to E, and then H, and then we get to G. So we've gone from B to A, and then down to F, and then across to E, and then up to H, and then along to G. The problem we've now got is that all the nodes connecting to G are already in the path, so we would stall. Let's see what would happen if we, instead of going from H to G, we had gone from B to A to F to E to H, and then on to C instead. From C we could have got to D. However, when we get to D, the nodes connected to D, i.e. C, H and E, are already connected, so again we would stall. We would still need to include G and get back to our start point of B. Now I suppose we could have a possible solution where we add on D to H again, and that would get us then to G, and then that 12 back to B. So we could add those extra arcs, giving us an upper bound of 58, which gives a solution to the practical problem because we've repeated arcs. If we found an upper bound using the nearest neighbour algorithm, we may seek to improve upon this, as we can sometimes use common sense to find shortcuts that produce a better solution by improving one section of the cycle. Particularly where, during the nearest neighbour algorithm, in the last few choices for arcs, we may have found that we were forced to use longer arcs than we really wanted to. Using the Hood algorithm on this network starting at A would give us, so A is nearest neighbour to B, nearest neighbour to G, given A is already taken, nearest neighbour to H, then nearest neighbour to C, to D, and then that goes on to being nearest neighbour to E, closest to F, and then we are forced to take the very long arc to A, giving us a total weight of 79. So we didn't have a lot of choice about choosing that one. And when we got to D, again, because we'd already chosen A, B, C, D and so on, or the other nodes that connected to D, we were forced to take this long arc of 15. So the longest arcs were in that sequence: D, E, F and A, with a 15, a 10 and that 25, which, if you note, add up to 50 out of a total of 79. If we can, if you like, reschedule that part of the tour, we would be able to improve on the solution that the nearest neighbour algorithm gave us. So, by inspection, we can see that if we had gone from D perhaps down to F and used this 16, so gone in that direction next, and then we could have used F to E, and then E back to A. So let's see if that's any better. Well, we've got a 16 there, which is quite high, and the 10 to the E, but then the E to A is only 12, and actually that totals 38. If we were to replace those sections then with the tour A, B, G, H, C and then the D, F, E, A, we would have an improved upper bound of 67 compared to that 79. Remembering that we're trying to get the smallest upper bound possible. This is the last video of the Graphs and Network 4 series.